Hi, good afternoon to all. Is the presentation visible? Yeah, okay. Thank you, Purnashri. So we'll start today's class. So this today's class, what we are going to see is a continuation of last class. Okay. So what we had seen in last class, I'll give you a recap. We had seen about course, acquisition codes, precision codes, encrypted Y codes, L1 frequency, L2 frequency, code pseudo ranges, satellite signal structures and its types, navigation message and its bits and byte informations. This is what we had seen in the last class. And the next topic in this presentation is about signal processing. How the signals are being processed at the satellite end and at the user end, and what are the different techniques being used for signal processing, that we are going to see in this session. Okay, let's go to signal processing. So the signals that are emitted from the satellite mostly consists of three components that are being represented in three different formats. One is L1 C bar A and D, another one L1 Y and D, third one L2 Y and D. So these three components in the symbolic form will be received from the satellite to either the monitoring control stations or to the individual users. So this received a C bar A code signal on L1 will be twice as powerful as that of Y code on L1. So if you see L1, it is a L1 band or L1 frequency on each of the satellites, the C bar A code signal will be twice as powerful as that of Y codes. And the same ratio exists between Y code signals on L1 and L2. So if you see an L1 and L2 blocks in signals, the Y code will be having same ratio. Here if it is 1000 megahertz, there also it will be 1000 megahertz. So this is the code, Y code signal strength. So presently what we use is that the block 2 satellites that transmits with about 6 decibels more power, either the 2A, 2R or 2F, all transmits with having a 6 decibel more power. So however, the nominal strength of each of the signals can be increased by using some processing techniques at your GPS receiver. So the recovery of these signal components needs some reconstruction of the carrier wave and extraction of the codes for getting the information of satellite clock readings and the navigation message. So here is a table which gives the strength reduction at L1 and L2 bands. If the signal is received in this C bar A code or Y codes measured in decibels. So the signal can be reduced with a range of about 156, minus 156 to minus 160 decibels in L1 band, and in L2 band we don't use C bar A codes, so it is nil always. So in Y codes, if you take specific Y codes, when it is being used as signal processed, the signal strength reduction can be from minus 159 to minus 163 in L1, and in L2 it is minus 162 to minus 166. So this is how the signal strength varies. So what is the principle of signal processing? Is that we have a carrier signal, we have a message signal, and this carrier and message are being coded within pseudo range noise codes, or we call it as PRN codes. With that, they are being added onto the satellite, and these satellites gives three different components. As said, L1CAD in a combination, L1YD in another combination, L2YD in the third combination. So all these signal components are being transmitted from the satellite to the receivers. It could be your user, it could be your monitoring station, or it could be a control station. So the receiver will decode it back by using appropriate PRN codes with the help of a carrier and message. So this is how signal processing takes place in GPS. So here is a small design of your receiver, how the receiver should be. There are many types of receivers available in the market that are used for different purposes, namely navigation, surveying, time transfer with different features. So for all these things, an omnidirectional antenna which is present in the satellite is helpful. So always the choice of your antenna should be an omnidirectional, since the omnidirectional antenna will transmit the signals in all the directions, 360 degrees. The omnidirectional antenna will receive the signals of all satellites above the horizon, and after pre-amplification transmit it to the radio frequency section, which is RF section. Then the signals are resistant to interference because the PRN codes are unique, which are being produced or which are being generated for each satellite, and will have very low cross correlations. So the antenna could be designed only for L1. It could be designed only for L1, or it could be designed for L1 and L2 also. So in most of the GPS receivers, which are omnidirectional, which uses omnidirectional antennas, are made up of microstrip antennas. So you can say I highlighted. Microstrip antennas are the mostly available antennas nowadays, which are used in GPS receivers. So this explains you a block diagram of a basic concept of a receiver unit. At your receiver, either your controlling station or at your user segment, you'll be using a control device which gives directions to the RF section and gets information from the microprocessor. So bidirectional. And this RF section and microprocessor gets the signals information through the antenna, only through the antenna, because it's an one-way communication. We'll be getting informations of only through antenna. So antenna is given to RF section. So if any information is to be stored, for example, if the location has to be stored, if navigation has to be stored, if any land surveying has to be stored, we can store it by using a storage device, either a RAM or a ROM, or any external devices can be used for storing informations of that particular location or whatever we want. Either if you want to store the time, you can store it. If you want to find the latitude, longitude, altitude positioning of satellites, you can store it. And all these things will be working only when we give a power supply. So power supply is your booster, or power supply is your feeding path to the whole receiver unit. So what are the parameters to be considered, and what are the different materials used in different blocks that we are going to see in this slide. Okay. So one of the most important design criteria of the antenna is its sensitivity to the phase center. The electronic center should be as close to its geometric center, since they are insensitive to rotation and inclination. So it should be very closer to the geometric center where we do all these computations. This is quite particularly important in the case of kinematic applications, because always the receiver or the user will be in motion. So as close as to the geometric center will give us more high efficiency or more accurate positioning. So additionally, the antenna should also have a gain pattern which filters low elevation or multipath signals. If there arises any interference due to multipath signals, it should be filtered out. At present, the performance is being achieved by this performance is being achieved by choke ring antennas, and the microprocessor, which is the main processing unit in your GPS receiver, will have the control over the entire system that enables real-time navigation and surveying. The control device always provides your interactive communication with the receivers, and the commands can be given through the microprocessor either in diagnostic or in any other message displays. So always the control device can be taken as usually your keyboard unit. Always can give commands through that. We'll be having a storage device, I said earlier, for storing any informations or storing the observed values, such that if in future if it is required, we can process it. So some of the types used for storage are your external computers, PCM, CIA cards, microchips, non-volatile storage elements, all being used as a storage. And many receivers will have a power supply inbuilt. Only in some cases they are being connected to external batteries or external power supplying agents. Next is the choice of radio frequency section. Always the radio frequency section is heart of the receiver. After the signal input from the antenna is obtained, the segregation of the signals is achieved by RF section. Usually we'll be using an C bar A codes. And there is another method also to distinguish between the satellites, is that by using a monitoring of Doppler shift, which will generally give the difference between the two satellites in space. The RF section always processes the incoming signals, separates the channel, and it segregates into two different parts. One is with a single frequency unit, another with the dual frequency unit having L1 in single frequency unit and L1 and L2 in dual frequency unit. The data always collected by the dual frequency unit will enable a combination where anospheric refraction can be eliminated. What are the refractions due to ionosphere can be eliminated by using this dual frequency receivers. Whereas an important feature of the RF section is that the number of channel determination. If the number of channels can be determined easily, then the tracking of the number of satellites can also be done simultaneously. Then next, the most important design for an receiver is that most receivers assign one satellite each to a physical channel where the satellites can be continuously tracked. There are multi-channel receivers also, which can provide us more accurate information and less sensitivity to loss of signals, which occurs due to inter-channel biasing. And nowadays, all the modern receivers that we are using uses biasing circuits which virtually eliminate the calibration. These receivers are always less expensive, but sometimes they are slower. So this can be used only in surveying. And we have another technique, another type of receivers called hybrid receivers, which use the combination of all the techniques for selecting the radio frequencies. Always the radio frequency section will have oscillators that are used to generate reference frequencies, multipliers to obtain higher frequencies where we get the carrier, then filters to eliminate the undesired frequencies, and mixers. We'll be using an appropriate filter to eliminate the unwanted frequencies which is arising from the satellite. So mixers will create two oscillations, Y1 and Y2, with different amplitudes A1 and A2 at different frequencies F1 and F2. So we can write the equation as Y will be always equal to Y1, Y2, so which is A1 cos F1 of t into A2 cos F2 of t. This is the function representation of a sinusoidal signal. So A1 A2 by 2 cos of F1 minus F2 of t plus cos of F1 plus F2 of t, where F1 minus F2 is the lowest frequency part and F1 plus F2 is the highest frequency part. So in this, when we apply a low pass filter, always the low pass filter will tend to pass only the lower frequencies and eliminating the higher frequencies. Okay, so then if the difference F1 and F2 is obtained as the intermediate frequency, the difference F1 F2 between the frequencies is always called beat frequency or the intermediate frequency, that is used to easily calculate the higher frequencies. So all this thing you would have studied in your communication system using of an higher frequency range, which converts your high frequency range into a low frequency RF frequency range. So there is a recently developed GPS receiver which converts the RF signals directly into digital information. This is a recent development. The RF information directly into digital information in the form of binary zeros and ones, which may not require an IF part in between, intermediate frequency part in between. So which was developed by using a silicon germanium powered GPS. This does this function. So after the radio frequency section, we have here we have the diagram. After the radio frequency section or the RF section, we have a microprocessor. So what type of processing is done, or what type of processing is done, that we are going to see in processing techniques. So in processing techniques, the actual pseudo range measurements are performed measuring the actual range of presence of the GPS receiver or the satellite. They are being performed in using a tracking loop circuits. And due to the motion of satellites, the received signals are always Doppler shifted. That means the tracking loops must be tuned within a frequency range such that they determine the DLL, delay lock loop, by using some corresponding code correlation techniques. So after removing the PRN, pseudo random noise codes. After removing this PRN or the pseudo random noise codes from the incoming signal, some filtering is to be carried out. So where the Doppler shifted unmodulated wave can be obtained. Then this carrier wave is passed through the PLL phase lock loop where the signal is compared with a carrier generated in the receiver to give the phase offset between the two signals. So this is how the processing takes place. The code correlation techniques provide all the components of the satellite signal like satellite clock reading, navigation message, unmodulated carrier. And how this correlation technique is being performed is that by using two different steps. One is the first step is a reference carrier is generated in the receiver, which is then biphase modulated. Why do we use biphase modulated? Is that we had used in our we had said in the previous class that biphase modulation is used. So we'll be using an biphase modulation in accordance with the receiver's reference carrier signal. So the second step is that the resulting reference signal is correlated with the received satellite signal and are shifted with respect to time so that they can be matched optimally. Correlation, second step. And in order to determine the maximum correlation more accurately, two correlators with one chip spacing are normally used. The accuracy is always measured if the spacing of the two correlators are reduced. A narrow correlator spacing technique is standard in high performance coarse or acquisition code receivers. The time shift resulting from the correlation corresponds to the satellite travel time from the satellite antenna, so that the phase center of the receiving antenna where we can have our clock biases to be neglected. So under clock bias neglecting segment, we can use this narrow correlator spacing technique performing high performance. After the removal of PRN codes, we will have the received signal that still contains some messages, which we call it as navigation message, that can be decoded and eliminated by a high pass filtering. The final result will be our Doppler shifted carrier on which a phase measurement can be performed. Since a PRN code is required, the code correlation technique is generally applicable only to C bar A code with only L1 carrier being reconstructed. If Y code is available, both the carriers can be reconstructed by the code correlation technique. However, we'll be using C bar A code to lock onto the signal and initialize the tracking loop. Always we'll be using C bar A codes mostly to reconstruct our signal being obtained. This is performed in short duration since always our C bar A codes repeats for every millisecond, and the computation is also very much simpler. So when you go for Y codes, it repeats only after 1 week. So the result of the C bar A code correlation is decoded with the navigation message that contains HOW how in each subframe that has the V code for signal matching. And without the knowledge of the Y codes, one cannot define the techniques to reconstruct the unmodulated carrier waves from which the phase of the phase carrier is to be measured. Most receivers always provide a hybrid technique where the L1 carrier is reconstructed by code correlation using C bar A code, and the quasi-codeless technique is applied to reconstruct the L2 carrier. Always in the processing side, if you want to reconstruct an CA code, we'll be using L1 carrier, and if you want to reconstruct an Y code, we'll be using L1 and L2 both. And here are listed some 4 different techniques that are used for processing the signals with anti-spoofing AS. So the first technique is the squaring technique. There are 4 techniques: squaring technique, cross correlation technique, code correlation plus squaring technique, and the Z tracking technique. We'll see all these 4 techniques one by one and where they are being used in processing the signals of satellite. The squaring technique was first given by C. Councilman in the year 1981. This is based on auto-correlating the received signal. Here the received signal is multiplied with itself and all the modulations are removed. This happens with a 180 degree. It's not 1800. I will change it. It's 180 degree. That's what I'm changing it to 180 degree. It's not 1800, 180. This happens within 180 degree phase shift during modulation, and it is equivalent to the change in the sign of the signal. The result is the unmodulated carrier with twice the frequency and thus half the wavelength. This is more difficult to resolve the ambiguities of the squared signals with half wavelength. Indeed, this has some advantages that it is independent of PRN codes, and still we have a drawback of the squaring technique is that the satellite clock and the satellite orbit information are lost during processing. If we do processing of using the squaring technique, the satellite clock's information and the satellite orbit information are cannot be retrieved or they are being lost forever. So here the SNR is substantially reduced, always reduced by using squaring technique, and compared to the code correlation technique, how much SNR we can reduce is that it is reduced by 30 decibels. So we go for the next technique, cross correlation technique, introduced by P. McDoran in the year 1985, based on the fact that the unknown Y code is identical on both the carriers, that enables cross correlation of L1 and L2. Due to the frequency dependence propagation of electromagnetic waves through the ionosphere, Y code on L2 is slightly slower than Y code on L1. And the time delay necessary to match the L1 signal and the L2 signal in the receiver is a measure of the travel time difference between two signals. The delay of the L2 signal is variable that can be adjusted appropriately to achieve maximum correlation between L1 and L2. The observables resulting from the correlation process are the range difference between the two signals obtained from the time delay of Y code on the two carriers like L1Y, L2Y, and the phase difference. So this power of L1 ranging is always twice that of corresponding L2, as said earlier. And the cross correlation of L1 and L2 leads to an improvement of 3 decibels compared to squaring of L2. So comparatively, when we use this, we get a signal to noise ratio degradation of 27 decibels. So where RL2 can be calculated from RL1 of C bar A plus RL2 of Y minus RL1 of Y. And the phase difference can be obtained by phase of L1 C bar A plus phase of L2 minus phase of L1. Next method is the code correlation plus squaring technique. Here in code correlation, we'll be using a split spectrum mechanism which will give better anti-jamming capability, which was introduced by Keegan in the year 1990. A simpler technique where the squaring technique is added with an code-aided mechanism that does squaring of the received Y code on the L2 signal with locally generated precision code. So this correlation is possible as Y code originates from the modulo 2 addition of the P code with encrypted W codes. Always the chipping rate of W code is 20 times less than the frequency of Y code, as we had wrote in a table in the last class. Y code, P code table we had wrote how to find the chipping rates. There exists Y code portions which are identical to the original P code portions. The duplicate of the P code is shifted to match with the underlying P code portion of the satellite Y code. After correlation, a low pass filter is applied by narrowing the bandwidth, and subsequently the signal is squared to write the signal of the code. This technique provides a code range good code range because of squaring half wavelength carrier phase. The correlation with the P code yields a better jamming immunity, which we call it as anti-jamming capability, with an improved multipath performance. The subsequent squaring results in 20 times more power, so which is approximately 13 decibels than by directly squaring the Y code signal. And signal to noise ratio degradation of 70 decibel occurs compared to the code correlation technique. Next is the Z tracking technique, which was given by Ashaji and Lawrence in the year 1992, which had used a quasi-codeless technique where the Y code on both L1 and L2 signals are separately correlated with a receiver generated due to the replica of P codes. Since there is a separation on L1 and L2, W code can be easily performed. Therefore, the carriers on each frequency also contain the encrypted code. At any particular instance with enough integration of signal, the encrypted signal bit can be estimated for each frequency and can be fed to the another frequency. So this estimation is used to remove the encrypted code from the signal at receivers. The integration performed by the low pass filter tends to reduce the bandwidth of the encrypting W codes such that there would be no need of the W code further in synchronization. In anti-spoofing or the AES, the removal of encrypting codes leads to same signals where the code ranges and full wavelength L1 and L2 carrier phases are obtained. Compared to the previous code correlation plus squaring technique, the SNR is improved by 3 decibels. However, when we compare with the code correlation technique, an SNR degradation of 14 dB occurs. So depending upon the requirement, we can use any of these 4 approaches in any technique where we want to process. So all the 4 approaches recover the L2 carrier signals in the process of anti-spoofing. Without exception, no codes or quasi-code techniques recovers GPS signal information as well as the code correlation technique. So nowadays, if you want to have an anti-jamming signals or signals to be obtained from an jamming devices, we can use an more sensitive GPS receiver. And nowadays, mostly the geodetic receivers uses Z tracking technique for processing of signals. So here is a small comparison of the technique versus its decibel. Signal to noise ratio degradation. One is the squaring minus 30 decibels, cross correlation minus 27 decibels, code correlation plus squaring minus 17, Z tracking minus 14. All these are being compared with your code correlation method. So here is a 4 comparisons in terms of operation and its output. First, squaring will be using a modulator in the operation which uses Y code only on L2, and in the output we will be getting no code range, only the phase difference of that L2. You can see the first program. Technique input operation output. If this is the operation, this would be your output. Next is the cross correlation. So where L1 and L2 of Y code are variably delayed will give us phi L2 minus phi L1 and RL2 of Y minus RL1 of Y. So this block diagram will give you an illustrative information of what we had seen of the topics of squaring, cross correlation, code correlation, plus squaring and Z tracking. So then code correlation plus squaring. In code correlation plus squaring, we will be using two different codes. One is Y code on L2 and P code duplicate or replica of P code to be modulated over a modular 2 addition given to low pass filter and again modular 2 addition. Then we'll be getting phi L2 lambda L2 by 2 over RL2 P. This P is to obtain your precision code. Next, in the Z tracking technique, we'll be having P codes in duplicate or in replica, and we'll be having Y code on L1 and Y code on L2. So here you can see the Z symbol. Okay, see this is your Z symbol. So this is why this is called as Z technique. In order to realize phi L1 RL1 of Y, phi L2 RL2 of Y. So this will give us a feedback register. All these are being considered when anti-spoofing is turned on. So these are the references. If you have any questions, type in the chat box. I'll give you 5 or 10 minutes time for this presentation. And Yeah, welcome to the second part of unit number 3 in global positioning systems. First of all, I'll give you an outline of what is present in this part 2 of unit number 3. The first topic deals with tracking the networks, followed by ephemeris. There are three different ephemeris. One is having almanac data, second one broadcast ephemeris, then precise ephemeris. After this types of ephemeris, we'll be seeing data combinations. Data combinations like linear phase combinations, linear combinations with integer number, linear combinations with the real numbers, and how to take care of code pseudo range smoothing. And the last topic will be the OTF, on the fly ambiguity. So let us start the presentation. First is the tracking networks. Let us see the objective and strategies of this tracking networks. What makes us to track a network? Okay. So the official orbit determination for GPS satellites is based on the observations at 5 different monitoring stations present in the control segment. So where the broadcasting of FEDMS for Block 1 satellite was done, which used CCM clocks, where uh, three times the information were uploaded, the timing information were uploaded per day. So per one day, the uploading information was three times only. So which had given an accurate information of the ephemeris of about 5 meters only. Accuracy level was up to 5 meters. So in Block 2 satellites, they had used an accuracy of about 1 meter, plus or minus 1 meter. However, an orbital accuracy of 20 centimeter is required for specific missions of TOPEX or Poseidon in order to obtain accuracy at a level of 10 power minus 9. The Block 2 satellites used this accuracy of in the order of 1 meter, but we require an accuracy of 10 power 9 meter, 10 power 9 nanometer. So in order to obtain that, the geodetic community made independent changes in the Department of Defense. So thus the need of civil tracking came into existence, where the minimum number of sites in the global network is given as 6, having that at least 2 satellites should be tracked simultaneously at any time from 2 different sites. So here comes the role of global networks. The global networks resulted in high accuracy and reliability of the orbits as compared to those determined from the regional networks. A tie-up of the orbital system to the terrestrial reference frames was achieved by the co-location of GPS receivers with VLBI and SLR trackers. So the next objective and strategy is that the distribution of the GPS sites was essential to achieve high accuracy. There are two different approaches that are to be compared. The first one is the sites are regularly distributed around the globe, and in the second case is that each network site is surrounded by a cluster of additional points to facilitate ambiguity resolution, and then strengthening the solution of the orbital parameters by a factor of 3 to 5. Apart from this, the GPS control segment, several networks have been established for orbit determination. Some networks are at a regional level, some networks are at continental size levels of Australian, such as the Australian GPS Orbit Determination Network. And however, the first global orbit tracking equipment, GOTEX, was performed in the fall season of 1988, aiming at co-location of GPS data with the existing VLB and SLR sites. The data always should permit an accurate tie-up with the WGS 84 system, which is widely used, and the VLBI and SLR systems. About 25 sites are distributed worldwide that will operate with the 3 weeks of campaign. A joint operation of the Cooperative International GPS Network, CIG net, was operated by the US National Geodetic Survey with tracking stations located at VLB sites. This service was started in 1988 with 8 stations in North America, Europe and Japan altogether. Then in 1991, there were already 20 globally distributed stations were participating for this tracking. Some of the examples of the global networks are 30 more stations were added to the existing CIG net in order to trace the information of data and or global orbital positioning. In 1990, International Association of Geodesy (IAG) decided to install an RGS, International GPS Service for Geodynamics. And after a test campaign in the 1994 in January 1st, this was being dedicated for geodynamic applications in order to determine the orbital positioning with higher accuracies. This IGS, there is a typing mistake, it's not RGS, it should be IGS. I'll change it. IGS. International GPS for Geodynamics. The IGS is always headed by the Central Bureau, which is located at the JPL in USA, Jet Propulsion Laboratory. So this tracking of the network, I'll show in a diagram in the applications of JPL that had consisted of more than 220 globally distributed GPS satellites tracking together for in coordination in order to determine velocities related to ITRF. So these IGS stations, International GPS Service for Geodynamics, collects the code ranges and carrier phases from all the satellites in viewing with dual frequency receivers. We had said that L1 and L2 will come under dual frequency receiver. So then these data are analyzed independently by 7 agencies and are daily archived in receiver and software independent exchange formats. RINEX and SYNEX are being used by global and regional data centers. Today, this IGS routinely provides high quality orbits for all GPS satellites that provide predicted orbits with an accuracy of about 1 meter in almost real time applications. Having having a delay of approximately 2 days in order to determine the final solution. So the accuracy of the final solution is estimated to be about plus or minus 5 centimeter, and also the raw tracking data, the satellite clock parameters, earth orientation parameters, and the other data like ionospheric and tropospheric information also can be determined through this service of tracking. Then coming to the next topic is the ephemeris. There are 3 sets of data available to determine the position, velocity, vector of the satellites in terrestrial reference frame. The first set of data is your almanac data. Second one is the broadcast ephemeris. Third one, precise ephemeris. So this almanac can be determined for a few kilometers. Depending upon the age of the data, we can find it. Second one, the broadcast ephemeris can be determined for around 1 meter, or even better than that. And the third one is the precise ephemeris set of data in the range of 0.05 to 0.20 meter, depending upon the delay of the signal. So here is an information about the almanac data. What does this almanac data provides to the user, provides to the satellite also. So every satellite will be given an satellite ID by using a PRN. So it is represented as ID, parameter ID, satellite PRN number, week, it indicates the current GPS week. T alpha is the reference epoch in seconds within the current week. Square root of A is the square root of the semi-major axis measured in meters. E is your eccentricity of the ellipse being used. M0 is the mean anomaly at reference epoch. Omega is the argument of perigee. Sigma is the inclination offset from 0.3 semicircles or 54 degree is your approximate value. L0 is the longitude of the node at weekly epoch. Every week it will give an epoch value. Omega dot is your drift of the nodes, right ascension per second. A0 is the satellite clock offset in seconds. A1 is the satellite clock drift. So all these informations can be obtained by the almanac data. Okay. So the purpose of the almanac data is to provide the user with less precise data to facilitate receiver service, in order to have the satellite searching for planning tasks such as computation of the visibility charts. So this is a visibility chart. The almanac data are updated at least every 6 days and are broadcasted as a part of the satellite message. Every 6 days once, at least 6 days once, the almanac data will be reset or it will be updated. The almanac message will contain parameters for the orbit, satellite clock correction, and all angles expressed in semicircles. So this is how do we find the almanac data. Keplerian parameters m naught plus n of t minus ta I m, you can see m is the mean anomaly at reference epoch. You can find it. I, you can find 54 plus tau I, 54 plus the inclination offset from 0.3 semicircle, which is this. You can find L. Hey, TV sound L can be found out L naught plus drift t minus t alpha minus omega e t minus t naught. So where this omega e can be obtained from this value 7292115.1467 into 10 power minus 11 radian per second. You can find the satellite clock bias also by this formula a naught plus a1 of t minus ta. You can see that ta is the reference epoch in seconds within the current week. E is the eccentricity. A naught is the satellite clock offset in seconds. A1 is the satellite clock drift. So using this, we can calculate easily all the almanac data. So this almanac data are also available from variety of information services from NIS, and they can be packed into YUMA or the SEM format. Next is the broadcast ephemeris. The broadcast ephemeris are based on the observations at the monitor stations of the GPS control segment. These are the parameters we had seen already. ID is the satellite PRN number. Week is the current GPS week. T ephemeris reference epoch. Square root of A is square root of semi-major axis in meters. Eccentricity. Omega naught is the argument of perigee. I naught is inclination. L naught is the longitude of the node at weekly epoch. M naught is the mean anomaly at reference epoch. Del n is the mean motion difference. I is the rate of inclination angle. Sigma dot is the rate of node's right ascension in broadcast ephemeris. CUC, CUS is the correction coefficients of argument of perigee. CRC, CRS is the correction coefficients with respect to geocentric distance. CIC, CIS are correction coefficients with respect to inclination. So CU is argument of perigee, CR is your geocentric, and CI is your inclination. So next is your TC, satellite clock reference epoch. A0 satellite clock offset, A1 satellite clock drift, A2 satellite clock frequency drift. And additional tracking data are entered with the help of a Kalman filter, and the improved orbits are used for exploration. The master control station is responsible for the computation of ephemeris and uploading it to the satellites. The broadcast ephemeris are a part of the satellite message, which is essentially the ephemeris containing records of general information, the records of orbital information, records of the information of the satellite clock. These parameters are in block of orbital information or the reference epoch, which has 6 parameters to describe the Kepler ellipse. And there are 3 secular correction terms and 6 periodic correction terms. The correction terms always considered are perturbation effects, which are obtained due to the non-sphericity of the Earth, the direct tidal effect, and the solar radiation pressure. The ephemeris are broadcasted every hour, and they are broadcasted every hour, and during the prescribed period of approximately 4 hours are being used for approximation. In order to compute the satellite position at observational approach, the following quantities are to be determined. So how do we determine this? M is m naught plus square root of mu by a cube plus del n into t minus te. L is equal to L naught plus omega dot t minus te minus omega e t minus t naught. Omega can be obtained by omega naught plus cu cos of 2u plus cs sin of 2u. R can be determined by r naught plus crc cos 2u plus crs sin 2u. I can be obtained by I naught plus CIC cos 2u plus CIS sin 2u plus I t minus te, where this u can be computed by omega naught plus v, which is the argument of latitude. So further we can find the computation of the satellite clock as sigma s is equal to a naught plus a1 t minus tc plus a2 t minus tc squared in the second order. Coming to the next ephemeris is the precise ephemeris. The official precise orbits are produced by Naval Surface Warfare Center together with the NIMA, and these are based on observed data in the tracking network for the control segment. The post-mission orbits are available upon request. The most accurate orbital information is provided by the International GPS Service with a delay of about 2 weeks, which are less accurate information that is available after 2 days of observation. So whatever we get the data from the IG, yes, is always a delay of 15 days. So the precise FEWS consists of satellite positions and velocities at equidistant approaches with a typical spacing of data of 15 minutes each. The NGS is involved in distribution of precise GPS orbital data, where these data are being distributed in specific ASCII formats with SP1 and SP2 and their binary counterparts as ECF1 and ECF2 that contain the position and velocity data. These data almost occupies half of the storage amount, and the velocity data can be computed from the positional data by numerical differentiation. Uh, the instance of at around 10 o'clock can be recorded, and at 10:30 can be recorded, and the difference between that will give the velocity by the numerical differentiation. So for this, we'll be using Lagrange interpolation, that is used in determining the variable approach series, and the coefficients are determined and applied with a considerably longer series without updating the coefficients. This interpolation method is a fast procedure and can be easily programmed. So in 1989, the NGS decided to add GPS clock offset data into orbital formats, and in the second generation handled up to 85 satellites as compared to 35 in the first generation. Apart from the clock corrections, the files normally contained only positional data. However, a header flag allows for the inclusion of velocity data. The corresponding ASCII format is denoted as SP3, and the binary counterpart as ECF3 or EF18. So each NGS format will have a header having general information like approach interval, orbit, type, etc., followed by a data section for successive approaches. So these data are repeated for each and every satellite. The positions are given in kilometers always, and the velocities are also given in kilometers per second. The position and velocity vectors between the given approaches are obtained by interpolation, where Lagrange interpolation is based on polynomial based functions. The next topic is data combinations.
அங்க இருக்கிறது அவங்க வீட்டுல நீ வாங்கிட்டு வந்த டிவி 43 தானே இல்ல இப்ப எத்தனை 43 தானே அங்க இருக்கிறது ஐயோ பின்னாடி வச்சு ஆனா 43 தானே அங்க இருக்குது
Next topic is the data combinations. Yeah. Next topic is the data combinations. The informations observed by the GPS are obtained from the code information or the carrier wave in broadcast satellite signaling. So recalling the precision codes or the P codes that are being modulated on both L1 and L2, and where only C bar A is being modulated on L1. So keep in remembrance of this. So how do we measure all these things? Is that by using any of these techniques. So what we are going to do is that we are going to combine all these data into a single system, either in the form of linear phase combinations or in the field of code pseudo range smoothing. These are being computed. So what we are going to compute is that we are going to compute code ranges, which is RL1, L1's code range, RL2, L2's code range, phi L1, which is phase difference of L1, phi L2 is phase difference of L2 band, the carrier phases. Okay, sorry. Carrier phases are your phase L1, phase L2. Doppler shifts of L1 and L2 for a single approach. For this, there are two methods being developed: the linear combinations, the dual frequency data, and code range, pseudo range smoothing. First, let us see the linear phase combinations. So this linear phase combinations is given by phi is equal to n1 phi 1 plus n2 phi 2, where n1 and n2 are the arbitrary numbers that depends upon the signal information, which can be taken as n1 f1 t plus n2 f2 t. So if the frequencies are same, we can write it as ft. Therefore, f can be obtained as n1 f1 plus n2 f2, and we can find easily this value of f also. F can be obtained by the relation lambda is equal to c by f, which is known to all. Then considering a certain level of noise for the phases, the noise level increases for linear combination. So applying an error propagation law and assuming the same noise for both the phases, the noise of the linear combination can be amplified by a factor square root of n1 square plus n2 square to that of a single phase. To compute this error factor correctly, proper noise level must be taken into account. Okay. So for that, we can use either the integer numbers or you can use the real numbers, any of these two. If you use an integer numbers, the advantages is that with integer numbers, the ambiguities are being preserved. So how do we calculate that? Is by using this procedure. So take n1 and n2 as 1, such that we get phase difference phi L1 plus phi L2 is equal to phi L1 plus phi L2, and we are taking a leading difference. We assume that we have a leading difference. We can write it as phi L1 minus phi L2. There will be getting two linear combinations. One combination with integer numbers -1, another one is with +1. If we use +1, we get phi L1 plus phi L2. If you use -n1, we will be getting phi L1 minus phi L2. So the corresponding wavelengths can be calculated accordingly. As for lambda L1 plus L2 as 10.7 centimeter and lambda L1 minus L2 as 86.2 centimeter, where we call this phi L1 plus L2 as a narrow lane of frequency, phi L1 minus L2 as wide lane frequency or wide lane phase difference. And if we use integer numbers, instead of integer numbers, when we use real numbers, this is how we get the linear combinations of the datas. So if n1 is 1 and n2 is f of fl2 divided by fl1 in minus, we get this leading combination. So this leading to the combination, we get it as phi L1 L2 as phi L1 minus FL2 divided by FL1 into phi L2. So this is this combination of phi L1 minus FL2 divided by FL1 into phi L2 is used to reduce ionospheric effects. And there is another combination of this is that we take N1 as 1 and N2 as minus FL1 divided by FL2. This is also resulting in a leading combination such that phi L1 L2 will be phi L1 minus FL1 divided by FL2 of phi L2. So the drawback in this is that with real numbers compared to the integer type, the ambiguity is lost. Ambiguity is your complexity. Next is the code pseudo range smoothing. The objective of the code pseudo range smoothing is to show the principle of smoothing by means of phase pseudo ranges. This is an important issue in accurate real-time positioning. The code pseudo ranges of L1 with respect to time t1 and L2 with respect to time t2 for the carrier phase pseudo ranges can be obtained by this equation. Or t1 is equal to f L1 or L1 of t1 minus f frequency of L2 or L2 of t1 divided by FL1 plus FL2. Where this is formed for the code pseudo ranges of the wide lane signal. Keep in remembrance, this is always your pi L1 minus L2 is always your wide lane signal. Pi L1 plus L2 is your narrow lane signal. Now, all these smoothing algorithms are also applicable if only single frequency data are available. So the advantage of this procedure lies in the reduction of noise in the initial code pseudo ranges by averaging an arbitrary number of measured code ranges. This is the advantage of each and every data combination technique. Next is the OTF, on the fly ambiguity. This notation OTF reflects any type of rover motion. Rover in the sense any. நாலு மணி வரைக்கும் நாலு நாலு மணி வரைக்கும். The notation OTF reflects any type of rover motion. The rover in the sense motion of your satellite in space or in any of the celestial bodies or in any planets, which we call as rover. So this rover motion plays an important part ஹலோ சார் சொல்லுங்கள் சார். Yeah, the AROF, ambiguity resolution on the fly, and the OTF, on the fly, and the OTR, on the run, are different abbreviations but with the same meaning, that they are being used for kinematic representations. So in kinematic positioning, this OTF ambiguity plays a major role. So there were numerous techniques developed. There are numerous techniques being developed to deal with the kinematic cases. So code ranges were usually used to define the search space for kinematic applications. A relative code range position was used as the best estimate of the antenna location and the associated standard deviations that were used to define the size of the search space. The space was determined in several ways. Yes, for example, they used cube, they used cylinder, they used ellipsoid, and so on. In order to reduce the number of integer ambiguities, combinations were tested, different combinations were tested, code solutions were given for accurate possible measurements, that the receiver selection was an important parameter to be dealt. The availability of low noise, narrow correlator type code ranges was always an advantageous. Hey. The availability of low noise, narrow correlator type code ranges was always an advantageous thing, since they had a very low resolution in the order of 10 centimeter, as well as improved multipath reduction compared with the standard C bar A code receivers. The importance of this carrier phase wide lane is to be mentioned in the context of number of potential ambiguity combinations, that the observability of L1 carrier phase is clear. And the disadvantage of this using in wide lane is that the measurement of this information is noisier than L1. So they used many OTF implementations for wide lane to resolve integer ambiguities, and to use the resulting position to directly compute the ambiguities on L1 carrier phase data. Then the wide lane is were also extensively used for static applications where station occupation time is limited. For stationary applications, this wide lane system on the OTF was a very useful technique, where it had features like determination of initial solution, initial point determination, static point information, static position determination was being done exclusively. A feature of this ambiguity function is its insensitivity with respect to cycle slips. So as far as the search domain, either we search in a domain space or reduction of trials is concerned, there are several combinations of characteristics. So these are the characteristics of that. The initial position or the initial solution can be obtained by determining its position XYZ, latitude, longitude, and altitude with its accuracies sigma x, sigma y, sigma z. We can find the carrier solutions also for xy coordinates and accuracies of nj. sigma x, sigma y, sigma z, sigma nj. Then we can use it for searching domains, the test points of n-dimensional integer spaces, search space k sigma x, k sigma y, k sigma z, k sigma n, where n is your number of ambiguities, number of complexities which is being generated. So the determination of k could be always empirically and statistically determined. The reduction of trials can be obtained from the grid searches, either fine grid search or coarse grid search with respect to its signaling. Then you can find the double difference phase intersection with the statistical information of correlation of ambiguities. We can determine selection criterion with maximum ambiguity function and a minimum variances, acceptance criterions with the ratio of largest and second largest ambiguity function, ratio of smallest and second smallest variance sigma square. You can find the ambiguities function between the largest and the second largest, top two, and smallest and the second smallest variance of sigma square, sigma naught square, which is minimum two ratios. So the observational period of instantaneous potential with some durations can be determined over particular time duration. Then the data required is that either it is a single frequency or a dual frequency. Mostly we'll be using dual frequencies nowadays. And we can find either the phase alone or phase and the code. So your PRN codes. So the major tasks of the OTF ambiguity can be given in this. The first one is the ambiguity function method can be used, where minimizing the variance and selecting the appropriate criterion stands as your basic principle for minimizing the sum of squared residuals. If the position of the receiver is eliminated by using some mapping functions, then that will reflect in the ambiguities by either using this 6 methods.
Please. So
By these 6 approaches: ambiguity function method, least square ambiguity search, fast ambiguity resolution approach, fast ambiguity search filter, least square ambiguity decorrelation adjustment, ambiguity determination with the special constraints. So these are being obtained as your double difference phase intersection to reduce the number of trials, positioning from the 3 double differences with set of possible ambiguities, the geometric progression, and the intersection of the planes such that we get an appropriate position of the system. So all this plays a major role in the OTF ambiguities. So these are the references. The mostly referred is your Ben Hoffman, Wellenhoff, H. Linster, J. Collins, GPS Theory and Practice, 4th revised edition. GPS Satellite Surveying, Guide to GPS Positioning, Understanding GPS Principles and Applications, Modernization of Global Positioning System, GPS World, Mathematics of GPS, Life After SCA, GPS Theory and Applications, GPS for Geodesy, Introduction to GPS, Global Positioning System. Any questions you can put in the chat box. Kindly await, I will send you the attendance form in chat box. The attendance link is given in chat box. Kindly fill the form. Those who are filling, only for them attendance will be given. After completing the attendance, you can leave. After completing the feedback, you can leave. Hemalata, do not go out of the meeting. Wait, let others go. Hemalata, stay in the meeting.
Okay, sir.
Sir, 210 present, sir.
What, Satish Kumar? Now you came to the meeting and you're giving attendance. Fill the form.
No, sir, I got interrupted in between, sir, at 2:45,
Okay,
3:45.
okay. Fill this form. Did you get the link?
Yes, sir. I got it, sir. Thank you, sir.
Yes, Hemalata. Where you kept your receipt, ma? In a hostel room,
Hostel room,
Okay.
sir.
Why? Because since your hostel fees details is not updated in the server, it is unable to generate results for you. That is
Okay,
an
sir.
issue. So I can give you two solutions from my point.
Sir.
First one is that the thing
Okay,
is that
sir.
you need to come and take that receipt and show it to the appropriate chief warden's mail ID. You need to send.
Okay, sir.
Okay, this is a solution that I can give you, or request any of your friends in Kanjipuram, or if anybody is coming or if anybody is available, ask them to go to your
Sir.
room. With the help of warden, you can show your receipts. So these two options I have, or these two solutions. Do you have any other solution for this? If it is there, you can tell me.
No, sir. నేను వార్డెన్ కూడా కాల్ చేశాను సార్. మ్యామ్
Hmm.
ఏమైనా హెల్ప్ చేస్తారేమో, హాస్టల్లోనే ఉంటారు కదా అని కాల్ చేస్తే మ్యామ్ కూడా మా మా దగ్గర డీటెయిల్స్ ఏం లేవు, హాస్టల్ రూమ్లో ఉంటే మీరే వచ్చి తీసుకోవాలి అని వాళ్ళు చెప్పారు.
That's what. Or if you're able to come, e-pass is not mandatory. No e-pass. Nobody will be asking. But thing is that you need to travel from there. So that is an
Yeah, yes,
issue.
sir.
That's what I'm asking. If any friends who is available in Chennai or in Kanjipuram.
Bhargavi always there in Kanchipuram.
Okay, you request warden madam first. If instead of me, my friend will come and take the receipts and submit. Will that be okay? You ask first question to madam. If madam
Okay,
agrees,
sir.
next you need to ask your dear friend.
Okay, sir.
If that is the only solution I can give you for the time being.
Okay, sir. So
Because
not only for me, sir. So in our class, so many, nearly 10 to 15 members.
Okay, you.
10 to 15 members not given results,
Yeah.
sir.
Somebody has to help in this way only. No other go. They will be keeping their receipts, at least if they are done online transaction.
Sir.
With that the reference number they could have applied. For example, if you are done online transaction using some debit cards or net cards, that date and reference number if they give, or if you give, with that they will make a note and they'll cross check and I'll give you. But since you had paid through cash and not having the receipt copy or is date, at least if date at least is there, they'll verify. So that is the issue. So if any date is if date is available also, no issues.
I will try, sir. I will ask to ma'am and I will ask if she accepts. I will ask Bhargavi, sir.
Yeah. But you say where your receipt is present correctly to your friend, so that she can take it correctly.
Okay, sir.
What they will ask is that at the entrance they will ask purpose of visiting the college. Say I have to write that helping taking receipts, like that, taking receipts in hostel. Okay, then
Sir,
key room
possible
key
అవ్వకపోతే కాలేజ్కి వచ్చిన తర్వాతే రిజల్ట్స్ ఇస్తారా సార్?
college లో
ఇప్పుడు మీరు నాకు 2 ఆప్షన్స్ చెప్పారు కదా, అవి 2 పాసిబుల్ అవ్వకపోతే మళ్ళీ నేను కాలేజ్ రీఓపెన్ చేసిన తర్వాత వచ్చిన తర్వాత రిసిప్ట్ సబ్మిట్ చేస్తే అప్పుడే ఇస్తారా రిజల్ట్?
then only they'll clear. So that is an issue.
ఐడియా ఏమైనా ఉందా సార్ కాలేజ్ ఎప్పుడు ఓపెన్ చేస్తారు అని?
Only after government of Tamil Nadu clears. Yes, day before yesterday also from C section 2 students came to college. They took the receipts from their appropriate places, showed it, got clearances, everything they finished and got the results also. From my knowledge, 2 members came and went. So that's what I'm giving you an idea. You need not come. Request any of your friends in Kanjipuram or any of known persons. So that's what I'm asking. Or if they are even in Chennai, ask them.
Okay, sir. I will
But
try, sir.
but they should have your room key na. Room key.
It warden ma'am available means warden ma'am to ఉంటుంది సార్ maximum.
Okay, duplicate will be there with madam.
Yes, sir.
ఓకే ఓకే దెన్ యూ రిక్వెస్ట్ ఫస్ట్ మేడం మేడం ఈ నా ర్యాక్లో ఈ మధ్యలో నేను పెట్టాను బుక్ మధ్యలో అది మొత్తం తీసి నాకు పంపిస్తారని అడుగు మీ ఫ్రెండ్ మేడంని పంపిస్తే ఇంకా ఇంకా ఈజీగా ఉంటుందిగా
అవును సార్
కానీ మేడం హాస్టల్లో ఉండాలిగా అది ఇంకొక ఇబ్బంది ఉంది
చూస్తాం సార్ పాసిబుల్ అయితే నేను వస్తాను లేకపోతే ఎవరినైనా రిక్వెస్ట్ చేస్తాను
అదే
థ్యాంక్ యూ సార్
they will allow you if you are having ID card college ID card they will allow you inside okay va
ఓకే
but they should say that we are going to hostel for receipt taking
ఓకే సార్
okay ma'am
థ్యాంక్ యూ
or if there is any issues in entering the college premises say them to call me directly I'll inform to security also okay
ఓకే సార్
if college ID is there they'll allow you no issues yeah we need to write in register purpose of visiting what we're going to do that they need to write and if still issues are there say them to call me directly give my number whoever goes I'll talk to the security persons
ఓకే సార్
but make sure with the hostel warden the room key and room details madam takes care
ఓకే సార్
okay if anything is there you can let me know in WhatsApp
I will inform you by tomorrow, sir.
Okay no issues no if issues is solved no issue for me
Okay, sir.
okay so that you will get your results earlier thank you Hemalata
Thank you, sir.
okay
Sir, can I leave?
Google form filled
Yes, sir.
okay then you can leave
Thank you, sir.
thank you